Welcome to Unit 2 in our Nature of Science module. And in this particular unit, we're going to be looking at some of the myths about the nature of science. So here are some commonly held myths from your first reading, which you may want to, you could pause where we are now if you wanted to read the reading first from McComas, which is the principal elements of the nature of science, dispelling the myths, or you can go through the Unit 2 first and the recording of the unit and then maybe revisit some of them. Whatever is more comfortable for you. Some people like to hear the information before reading it and others prefer to read first and then listen. So it really is all about what works for you. So here's one common myth that we actually promote in school science a lot. And this whole idea that hypotheses become theories that in turn become laws. And this idea that there's a hierarchy. But really in science, all of these concepts are actually quite different. So the myth is that with increased evidence, so as we get more and more information, there's a developmental sequence through which scientific ideas pass on their way to final acceptance as mature laws. And we promote this idea in school science all the time. And this idea that something that's called a theory or a hypothesis it's less secure than a law. The accepted view is that theories and laws are very different kinds of knowledge. Laws are generalizations, principles, or patterns in nature, and theories are the explanations of those generalizations. So I don't know if you can remember from physics, around about year 10, when you did Newton's laws. You might be familiar with Newton's laws. And remember the F equals ma, or force equals mass times by acceleration. That's a law, and a law gives you some idea of a relationship between different components, how they're related. Whereas a theory, such as the theory of inertia, which describes how and why objects move or change their motion. So they're different kinds or different concepts. Here's another one. Scientific laws and other such ideas are absolute. And what we mean by that is that they never change. So this idea that even if you understand that scientific laws are equal importance to theories, they rarely appreciate that all knowledge in science is tentative. And what we mean by tentative is that it's able to change. So nothing is ever certain. We can't just assume that if we say it's science and it's a law, that it's going to be that way forever. And we tend to teach what we call final form science, where we promote the idea that, well, once it's done and it's in a textbook, it would never change. Okay, the third one, a general and universal scientific method exists. So this one, it's really common. So this is the one I was talking about in Unit 1, where when you go into high school and you start doing those pracs, where they're basically a recipe that you follow. So that notion that there's a common series of steps followed by all research scientists is one of the most pervasive myths of science. And here is a little sort of rundown. Here's your question. You do some research, form a hypothesis, do an experiment, get your data, and then form a conclusion. That it's a linear process. And here's those steps. And yes, those are all steps, but they don't necessarily go that way. So the accepted view is that those who study scientists at work have shown that no research method is applied universally. Close inspection will reveal that scientists approach and solve problems with imagination, creativity, prior knowledge, and perseverance. And that's a really important point to make, in that we don't actually conduct science in this way. There's always going to be backtracking. It's cyclical. Okay, so sometimes the experiment that we choose doesn't actually help us address our question, so we've got to go back. Sometimes the evidence that we gather doesn't align with our hypothesis, and yes, we can either support the hypothesis or not support it, but we may need to go back and revisit. Science is procedural more than creative, and again, this idea is very much, it's cemented in school science. But we know that only the creativity of the individual scientist permits the discovery of laws and the invention of theories. So theories aren't things that are out there that we go and find. They're things that are invented based on evidence, but they are still invented. If there was truly a single scientific method, two individuals with the same expertise could review the same facts and likely reach identical conclusions. And we know there's no guarantee of this, and in fact we know that it just doesn't happen because of the range, nature and application of creativity, which is a personal attribute. Science and its methods provide absolute proof. So we do know in science we can never prove anything 100%. So to prove something is actually not possible in science. And I know all our textbooks use that word prove. We can only ever disprove something. We can never 100% prove. So accumulated evidence can provide support, validation and substantiation for a law or a theory, but it will never prove those laws and theories to be true. And that's another term we don't tend to use in science is the term true. So we don't use prove and we don't use true, but you'll often find in a lot of publications, websites, textbooks, that those terms are used in science, and we should try to limit our use of those. So a hallmark of science is that it is subject to revision when new information is presented, and in actuality, the only truly conclusive knowledge produced by science results when a notion is falsified or disproven. So what this means is that no matter what scientific idea is considered, once disconfirming evidence begins to accumulate, at least we know that the notion is untrue. And again, there's that term true. So even I'm responsible for using the incorrect term or using it loosely, I should say. Science and its methods can answer all questions. And we know that that's just simply not possible. We can't answer moral questions, ethical questions, aesthetic, social or metaphysical questions with science alone. Okay, we can provide some insights into problems from these domains, but we can't actually answer those questions. So we know that science and its resulting technology may be able to clone mammals, but only society can decide whether such cloning is moral and ethical. Okay, so these applications are critical. So we can do all the discovering in the world, but if morally and ethically our discoveries are not fit, then we've got a major problem in science. So science has to work within a broader domain. Scientists are particularly objective. Now again, we have this notion of the scientist in the white coat who's never influenced by anything other than the data. But we know scientists are humans. They're no different in their level of objectivity than other professionals. Clearly, they employ careful analytical techniques of their evidence and procedures that they apply to arrive at conclusions. So we're not saying anything goes, but we do know that they are humans. This whole idea about theory-laden observations is really important because scientists have to try and be objective. I mean, they seek objectivity, but like all other humans, there is subjectivity to everything that they do. And previous ideas, okay, and previous experiences that they have had shapes the experiences they have in the future. So scientists, like all observers, hold myriad preconceptions and biases about the way the world operates. These notions, held in the subconscious, affect the ability of everyone to make observations. So we know it's impossible to collect and interpret facts without any bias. And remember this one, anyone that did my primary science course would remember this picture. So if you haven't done it before, have a look here and see, what do you see? Do you see a young woman or an old woman? Some people can see both, and particularly if you've seen this before, you are now probably able to see both straight away. But if you haven't seen it before, you will normally see one or the other. And even though the same evidence is presented, different people will see different things within that image. So the task demonstrates that people construct their own meaning for what they observe with their senses. What learners select depends on their prior knowledge, purpose, and beliefs. Yeah, that one might help you a bit more. I can see the young woman in this better than I can see the old, but again, it's a very individual. Here's another one. Experiments are the principal route to scientific knowledge. And again, school science has a little bit to answer for here. So throughout their school science careers, students are encouraged to associate science with experimentation. We know that virtually all hands-on experiences that students have in science class are called experiments, even if they would be more accurately labelled as technical procedures, explorations or activities. So a true experiment is going to basically look at two different variables and look at the effect of one on the other. But lots of things we do in school science are not that, and that's fine, but we do know though that experiments are sort of the privileged route to scientific knowledge. So true experimentation is very useful, so no one disputes that, but it is not the sole route to knowledge. So if we think about our observational sciences like astronomy, some of our paleontology, they basically rely very heavily on extensive observations rather than manipulating variables in experiments. So scientific knowledge is gained in a variety of ways, including observation, analysis, speculation, library investigation, and experimentation. This one's really interesting too. So science models represent reality. And again, our school science textbooks are very responsible for some of these notions. And you see that little image down the bottom there, different models of the atom. And one of the main things that we have to answer for with our textbooks is we provide these two-dimensional static images, which are only representations. They're supposed to facilitate understanding, and our students take them very literally. They think that that's sort of what they're going to actually see, or that these things they can actually, if they had a powerful enough microscope, they could see them. So the true nature of reality can never be known. So science is an invention as far as our theories and our models that we put forward. They're based on evidence, but they are still inventions. They were constructed by scientists to help aid in understanding. So this third point is really quite important. So it's doubtful that anyone seriously questions current atomic models, but it is important to remember that no one has ever seen an atom, in that we can't peer down a microscope and see an atom. We can have scanning images of atoms, but we can't actually see an atom. So a model works because it permits both predictions and explanations, but it is a construction. It's not a picture of reality, it's a construction. So that's a lot to hit you with in one little snippet. So it would be a really opportune time to reflect back on that reading, the McComas reading, because he goes through all of those points in a lot more detail. So now you've had a taster for them, you may wish to do that. And after you've done that, you may want to engage in this activity. So it's the second reading, not the McComas. So it's the Characteristics of Science reading by Clough and Kruse. I'd like you to read through that and then share your understanding of one aspect of the nature of science from the reading on the discussion board. So they talk about different ideas, all related to the types of things we've just looked at. We focused a lot on myths or things that are limiting, but the second reading focuses a lot more on aspects that we think are pretty spot on. So doing science well requires imagination and creativity, for example, is one. The generation and acceptance of scientific knowledge often takes much time is another. Science has a subjective aspect is another. So there's lots of different aspects, and I'd really like to know what you think of a particular aspect and share your understanding of it, or even your experiences with it, and where perhaps even your ideas might have changed, or they might have been myths about that particular aspect. Well-established science ideas are not easily abandoned. That's quite interesting too. So we'd really love for you to share your views about that before moving on to the next unit, where we're going to look at some criteria for defining science.